This is the next video in the chapter on advanced theories of bonding. We learned about how pi bonds consisted of an overlap of two p orbitals from two different atoms, and now we're going to apply that to understand resonance structures a little bit better. So we learned about resonance when we started to talk about Lewis structures, but have you noticed that the only time that we saw resonance when we had multiple bonds? The resonance structures featured placing that second or third bond in several different spots on a molecule. So for example, take the molecule NO3- or nitrate. There are three resonance structures for this molecule, which has a charge of -1. So there are three oxygens. Two of those oxygens we draw as singly bonded, and one of them we draw as doubly bonded, but we can't decide easily which oxygen to place the double bond on because all of those bond lengths are the same in real life. So instead, we draw three resonance structures. Oops, don't forget the charge. Placing that charge, or placing that double bond rather, on each of the oxygens in turn. So that resonance occurs because we have that multiple bond. And we know that when we have a multiple bond, that bond is going to consist of a sigma bond and a pi bond, wherever it occurs. And so the question is, which one of the nitrogen-oxygen bonds has the pi bond? Is it just one of them? Or is it all of them at the same time? And what we learned about resonance is that all of the structures need to be averaged together to represent what the true structures look like. So all three of the nitrogen-oxygen bonds have some pi bonding character. So let's zoom in a little bit on this structure. And I'm going to draw it from the side so it's easier to see, so that this is in the plane. Each of these oxygen orbitals, or oxygen atoms, in order to participate in a pi bond, has an available 2p orbital that can overlap with nitrogen. We would think about drawing the double bond as an overlap between two of these, but remember that there could be a double bond in any of these positions. So that means that there's an available 2p orbital in each of these positions. And the way that resonance works is that there is overlap between each of the oxygen orbitals and the central nitrogen. So there is some overlap between all four of these atoms, and that's why the double bond can be drawn in all three of those positions. It needs to be drawn as three resonance structures. So that nitrogen 2b orbital doesn't overlap with just one other. It overlaps with all of them. So we have a special name for this when the electrons in just one bond can be distributed over a large amount of space. This is called delocalized. If that electron pair is localized, it would look something like one of the structures we've drawn before, something like this. The electrons in this double bond are localized to the space between these two atoms, the carbon and the oxygen, because there's only one possible place to draw that bond. But in the nitrate anion, when there are three possible places to draw that bond, the electrons are delocalized between these four atoms, and they can exist throughout. So this is why We need to draw all of the resonance structures every time, because we need to accurately represent the delocalization of that electron pair. So that is our add-on to the end of the resonance story. That is, it is a delocalized electron pair.